In this video, we're going to take a look at forces and how we can figure them out. A force is any push or pull. A net force is the sum of all forces acting on an object at a given time. So if you take a look at something like arm wrestling, you're taking and combining both of the forces. It's not doing much, there's not much movement, but they're both there. So with a net force, you have forces present, but they might not amount to anything. Forces are always going to be measured in newtons, and 1 newton is 1 kilogram times meters per second squared. And when we talk about a newton, we're talking about the amount of net force required to accelerate a 1 kilogram object by 1 meter per second squared. It actually doesn't take much in order to do that. If you wanted to compare it, a newton is about the amount of force that an apple puts on your hand if you're just holding it in your hand. Let's say you're looking at a box that's sitting on the table. Well, we need to figure out what forces are present and how to draw the free body diagrams there. Free body diagram is a way of identifying the different forces that we have and getting them in the right place and how they affect the box. So we have a couple of different things that are going on here. First of all, before we can even do anything here, we have to figure out what are we identifying the forces on. And in this case, it's going to be the box. So we'll make sure that all of the forces are dealing with what's happening with the box. Yep, there's forces on the ground of the table. There's forces on the table from the box, but we're talking in this one, what's happening specifically with this box. So everything will relate to that. Once you've identified the object that you're looking for the forces, you're going to label any points of contact. So we'll take and we'll say, well, on here, there is really only one point of contact. And I'm going to highlight this on here. If you highlight it or not, it's not the end of the world, but it'll help identify exactly where a force might be applied. Then we're going to identify and label our contact and our non-contact forces. When we have a box here, we have gravity pulling down. I'm going to label this as the force of gravity. The force of gravity is a non-contact force. On the surface is pushing back on the gravity. If the table wasn't there, the force of gravity would just pull the box down. However, the table pushes back against that, and we call that a normal force. Once you have that drawn and labeled on there, then you'll sum the forces together by doing vector addition. And vector addition is a way of adding forces by taking the vectors that are drawn and putting them in the same location. And we call this the tip to tail method. Tip to tail vector addition. So we'll take this one exactly as it is and we'll move it over here, just like this. Usually you'll do this on a gridded paper or use a ruler for it. So I have my force of gravity here. Then I'm going to take my other arrow and I'm going to move it over, and the base of this arrow, I'm going to start at the tip of this arrow. So I'll start here, I'm going to go right back up there the same length, and the tip comes up here. Now there's no difference in what we have here. I drew it just a slight bit to the side so you could see the two separate arrows, but there's no difference here. We've got our gravitational force pulling down. We have our normal force pushing back up. Our start and our finish are in the same spot, so my net force is equal to 0. For this one, we're going to have a 20 Newton box with a push of 40 Newtons and friction of 30 Newtons. So we'll still do the same thing. We'll identify what we're putting the forces on, and for this will be this box. Most of the time it's a single object that you'll have. So this is my object that I'm dealing with. Everything else is happening, but we're looking at what's happening specifically on the box. Then we'll highlight our areas of contact. And so we know that the box is touching the floor here, and we know that the hands are touching the box there. This will help us to identify the forces that are acting on the box and where they are. Then we can label our contact and our non-contact forces. There's not a set rule as to which one you would do first. My preference is to do gravity first. So I'll take, and I know that my gravity, my box is a 20 Newton box. So that tells me that my gravity is 20 Newtons. Say force of gravity, 20 Newtons. I also know that my box is in contact with the floor. It's not falling. There's nothing that's there. It's just indicating that it's sitting on the floor. So that tells us that we have a normal force that is going 20 Newtons back up. The normal force is a reactionary force, and it's always matching the force of gravity. Sometimes it can be a little goofy with other forces that might be present, but here I've got my normal force, and that's also equal to 20 Newtons. This one is drawn from the place of contact here. I have a push of 40 Newtons. And so if you're drawing this on graph paper or gridded paper, you would have it go 4 boxes or whatever you would have set up for that. In this case, I'm just going to make sure it's about twice as long here. So there's 20, there's 40 Newtons going this way for my push. So I'll just say force of the push. It's some additional force that's being added into the system based on the push or pull that's happening. And then the other force that I have is friction, and that's going to be at the surface of the box and the table or floor as well. And so I'll still draw it from that spot. This one happens to be 30 Newtons, so I'm going to go about like this. Try and get it in there dark so I can see it in conjunction with the floor. And we'll say force of friction is 30 Newtons. So now I've drawn everything that's happening on there. My non-contact force is gravity. My contact force is the floor pushing back up for the normal force, the force of the push from the person here, and then the force of friction against the motion. So I've got these things that are happening. The addition here to what we had before, in the first example, we just had gravity and the normal force. Here we have a push, and friction always goes against the push or against the motion of the object. So we have these things here. We can still do the tip to tail method with this. So I'm going to do this just below here. And we're going to have my 40 Newton. You can do anything first. A lot of times I do gravity first. This one time I'm going to do the 40 Newton first. So it's that same line that comes down here, and I draw it just like it was. Then I'm going to take my next vector. It doesn't matter which one. And it's going to start at the tip of the first one. So here's the tip of the first one. I'm going to do gravity next. Again, it doesn't matter order. So I'll do gravity next here. Force of gravity. And then I'm going to do my force of friction. Coming back here, like that. Again, here's the tail of the first one to the tip. Then it goes to the tail of the second one to the tip. And then from the tip of that one, it goes to the tail of the third one, out to the tip. And then the last one that I haven't done yet is my normal force. I'm going up here, and it comes right here. So I started at this point, and I finished at this point. And the difference between the start and the finish is what gives me my resultant force here. So my resultant force, if I draw an arrow that starts at the start and goes out to the finish, my resultant vector here is the difference. We can do this with numbers also. If you're doing this on graph paper, you can easily count boxes. Here I'm going to add the numbers. I've got 40 across here. I've got 20 Newtons down. I've got 30 Newtons of friction going back this way. I've got 20 Newtons up. And so my remainder here, from here to here, is 10 Newtons in this spot there. If you look at it, I've got a 40 here and I've got 30 there. The difference is the 10. So here, my net force equals 10 newtons. So some of the things you're going to do is to take and draw your force diagrams on an object, and then use those force diagrams in order to draw your vector diagram and be able to figure out where it ends up and what your net force is. Now there's lots of ways forces might be added. If you use the tip to tail method, you can take and do all kinds of forces and get them to where they need to be and what your net force is. And if those are all your forces, you can say, well, here's my start and there's my finish, and you can draw out what you have, something like that. And doing that to scale will allow you to measure it well. You can also numerically combine your forces. So there's a couple of different ways that this might happen. If your forces are in the same direction exactly, you're going to add. If your forces are in opposite directions, you're going to subtract. If they're at a 90-degree angle, where you have something that's going up and something that's going to the side, you can tip to tail this, and if you have 90 degrees here, you know that from what you've done in math, that this would give you a hypotenuse, and you would have your force in your y direction, your force in your x direction, and your net force here. Well, when we see a triangle that's a 90-degree angle, we can use the Pythagorean theorem in order to figure that out. So if you know your force in the x direction and your force in the y direction, you can use this in order to get the net force or any other combination to be able to subtract out what you might need. The thing that's goofy is when you get to something that looks like this. And when you get to something that looks like this, in the end, you're going to get there. And in the middle, you're going to do some of this. But you'll need to break up each of these into their x and y components. So just like we did when we were talking about motion, if we had something that was shot off at an angle, you can do that same thing. So you might know, let's look at this force here. You might know that that force is going, let's do some different colors here. You would figure out, well, here's what's happening in the x direction for that force, and then here's what's happening in the y direction for that force. And if you know, which you should if there's information given here, what this theta is, again, you could go F in the x direction equals F net cosine theta. F in the y direction equals F net sine theta. And you have to be a little bit more particular about it, because depending on which angle you have, if you have this angle, you'd have cosine here and sine up here because this one's adjacent and that one's opposite. If you had a different angle, maybe you had the angle here, then you would have to reverse that. So you do have to pay attention to how your triangle is structured, what angle you have, and how to break it up. But if you have a bunch of different weird angles and you can get to your final x and your final y, then you can take this and figure out your net force overall. So then what else? Well, the equation that we use in order to determine the force that we have or how it impacts something is that force is equal to mass times acceleration. When we're looking at this force, we're looking at the net force that is acting on the object. That's measured in newtons. M is the mass, and it has to be measured in kilograms. And then A is acceleration, and that will be measured in meters per second squared. The mass has to be in kilograms because of what we talked earlier with the way that the newtons break down into kilograms times meters per second squared. The equation itself isn't anything that's too tricky. We're just multiplying. However, to get to the net force is that combination of the other forces to figure out what all's going on in a given situation. Note that force requires acceleration. Our net force, when we have a net force that's present, is going to cause a change in motion from what it's already doing. So we've got 3 different states of motion. The first one is at rest. It's not moving. The forces all balance out. There's no net force that's acting on it. So it is at rest. Another one is acceleration. It means that you have a net force. It's not equal to 0. Here at rest, your net force equals 0. Acceleration, your net force doesn't equal 0. It means that something is acting on it that's causing an acceleration. And depending on what that mass is and what that force is, the relationship between those will determine the acceleration. The last one is one that's a little bit tricky and we'll talk more about in class, and it's constant velocity. What this means is still our net force equals 0. However, with constant velocity, it means you have enough force to keep it moving forward and enough force going backward, an equal force going backward, that causes it to not accelerate. You experience this if you're driving a car and you have enough gas making it go forward. You're driving along at a constant rate, enough gas in the engine to make it go forward, but friction and air resistance and everything else is pushing against it. And so it balances out. You're still moving, but you're not accelerating.